Remember on the official test, there's only 12 pointers and 7 pointers. This is clearly 15 points. So this is off of either a practice test or a MyAP activity. This is actually a practice test from like 2017. So it's not terribly unrepresentative of what to expect, but it's a little bit longer. They say 15 minutes or 15 points in 25 minutes. That's, like I said, you'll get a 12-pointer, and they recommend 25 minutes for the 12-pointer on the exam. So I think that this is not unreasonable. But I think this test ended up being a little bit long for the actual time. Because I gave this as a test last year. I'd argue this probably a little bit long because there was also multiple choice in addition to this. Your test tomorrow is going to have one numerical styled FRQ like the second one and one like this. And then there will be a group of multiple choice questions. I need to emphasize to you that the multiple choice questions are really the place where you're going to break out your calculator and do calculations. That's pretty typical of the AP exam, that your calculation questions are going to be the multiple choice, and things that are going to have to be more thought out are going to be your FRQs. So figure we'd walk through and talk about all of this. I'm going to ask you guys to tell me your responses for different parts. I walked by and saw all sorts of papers, so I should be able to pick just about anybody, but I'll probably call for volunteers. We'll probably get more than one volunteer for any of the discussion questions. So let's start at the beginning. This problem, I think most of you recognize what's happening, but I want to make sure to emphasize this is the same question as the arrow and pumpkin question, really. It's got a collision that takes place during this portion of the problem. That's your conservation of momentum portion of the problem. And then there is a conservation of energy, a transition between energy being kinetic and energy being potential. In the pumpkin question, the arrow and pumpkin swung upwards. In this question, we used a spring to store that potential energy. But ultimately, very similar questions in what they're asking about. This one goes into more depth. So this style of question where there is a student claim and then you have to sound off against the claim. This is on the exam. You're going to have to do this. Part of it's called what they call qualitative quantitative translation. I'll say that again. Every test is going to have a QQ question, but it's a qualitative quantitative translation. And what they're trying to get at is, can you explain what's happening and reason out why other people's arguments are incorrect? You are going to have to do this on the exam. So since some mechanical energy is dissipated when the blocks stick together, the momentum of the two-block system decreases. I would say that this claim actually has two parts to it. Some of it sounds right. Some of it sounds maybe right or wrong. It's hard to know. Let's see. Indicate whether the claim is correct or incorrect. Raise your hand if you think the student is correct. Right. Raise your hand if you think they're incorrect. Right. Don't be afraid to stand up for what you believe in. But okay, so I have a lot of you who think it's incorrect. Who would like to explain what they think why it's incorrect? Okay.
The momentum of the system was conserved, and even though the collision may have reduced the amount of kinetic energy in block A and combined both blocks at a lesser shared velocity, the momentum was conserved.
All right. How many of you heard what Hayden had to say for that one? Okay. How many of your answers are similar? Okay. I think almost everything about what his answer has is good. I think it's missing something. Is there anybody who has an answer that has something slightly different or offers more information? Yes, ma'am? I think you have to say that. I think to get full credit, you have to indicate there's no external force during the collision. That would be how you would change something's energy, is an external force on the system. There is no external force in the system. So I think you have to say that. Saying it's a collision indicates that, but I don't think that's enough. I think your test graders want to know that you understand you need an external force in the system in order to change its energy. That's what the spring represents, an external force on the system. It takes the kinetic energy away from the blocks and puts it in the spring. All right. But we all agree incorrect. Well, we all agree now. When the blocks collide, the total momentum... another student, so some other Yago in the class has an idea too. When the blocks collide, the total momentum of the two-block system doesn't change, so the kinetic energy of the system must also be constant. Now, I don't know how you guys might explain this. How many of you think that this student is correct? Okay, how many of you think it's incorrect? All right. Would somebody like to offer their explanation? Yes, ma'am.
The kinetic energy is the constant it's decreasing.
Because? There should be a because.
Because some of the kinetic energy was transformed into another type of energy.
How many of you have something that says that not all the kinetic energy is conserved because some of it is converted into another type of energy? I think you have to say those things. I think you have to label the type of collision as well. In this case, you have no information to go on to actually be able to do a calculation to prove the kinetic energy is less. But I think because the blocks stick together, you could use vocabulary. You could say it's a perfectly inelastic collision, and therefore, the kinetic energy is reduced. So I think citing that's perfectly inelastic is probably a good source here. I don't think you have to go any further than that. But we'll go with incorrect again. All right, during the time interval from T3 to T4, is the magnitude of the acceleration of the two-block system increasing, decreasing, or constant? All right, so here we go. One finger, increasing. Two fingers, decreasing. Three fingers, constant. And don't look around the room, just look at me. Everybody hold up one of those options. One finger, two finger, or three finger. One finger for increasing, two finger for decreasing, three fingers for constant. Go, I want to see. Interesting choices around the room. We are split almost evenly into three camps. Did anybody, as their explanation as to why, talk about Hooke's law? Okay, well now we know why we have so many different answers. Right, we're talking about the time that it's pushing against the spring, right? That's T3 to T4 when it's coming to rest. It is the spring that's acting on them. Is the spring force getting bigger or smaller as the spring is compressed? The force from the spring is getting bigger the more the spring is compressed, right? Because X is how far the spring is compressed. So if X is getting bigger, the force from the spring must also be getting bigger. Well, Mr. Sheldon, what does that have to do with it? That's the only force acting on the system. So if X is getting bigger, the acceleration must also be getting bigger. So it is increasing. And I think the only way you get the answer correct and you get all the credit is to say all of those things. Yep.
Repeat the last part.
I think you first have to say that, well, I'll repeat the whole thing. I think you have to state, I think just writing this isn't probably enough, although you could do the substitution and then explain that as X gets bigger, the distance of the spring, the acceleration gets bigger. But I think you have to state both things. I think you have to state that a spring is governed by Hooke's law and that the force from the spring gets bigger as the compression gets bigger. That's the first thing you have to state. And the second thing is that Newton's second law. If the force on the box is getting bigger, the acceleration of the box must also be getting bigger. We good to go? A lot of writing, that's good. All right, so we're going to do this again. We're talking about positive work, negative work, or zero work on the block. One finger is positive work. Two fingers, negative work. Three fingers, zero. Ready? 1, 2, 3. How many fingers? Well, the class has settled on a more consistent answer here, and it's the right one. It is negative work. Good job. I think you have two explanations. Who has one? Go ahead.
The work done is in the opposite direction of the way the object is accelerating.
If you said the force is in the opposite direction of the way the object is accelerating, perfect. That would work out just fine. That is one explanation. I think that's great. There's another one. Or the other one would be to say a change in kinetic energy. it stops. So the change in kinetic energy goes from final to initial. It has kinetic energy, and then it's taken away, and that's why it's negative. So I think if you cite either one, that work is force times distance times the cosine of the angle, and reference the angle, or change in kinetic energy is going to be 0 minus something, that would be the other one. I think either of those would be a sufficient way that you could explain that it's negative. We need an explanation. All right. Are we good to keep going? All right, so we do this again, but now we have a spring with a higher spring constant. How does the new maximum spring distance in case 2 compare to case 1? How many of you said that D1 is going to be greater than D2? How many of you said that D2 is going to be greater than D1? Interesting. How many of you referenced this equals 1/2 kx squared as your reasoning? Who referenced that? Because we want to talk about this, because this is what you have to, I think, say. Is the amount of energy the spring going to store, is that going to change? Is there anything about the collision that's different? Are the masses of the blocks any different? Velocity of the blocks any different? So the blocks have the same amount of energy when they hit the spring, which means the spring has to hold the same amount of energy. But K is going to become a bigger value. If the spring is stiffer, that means that it's not going to be compressed as much. D2 is smaller than D1. It's not going to compress the spring as much. The spring is stiffer. It applies a greater force. So, all right. It really depends on how many questions have already occurred to whether you'll have something like this or not. This kind of part of the problem where they present you with more than one formula is pretty common. Sometimes they will ask for you to find out which one is true by showing the math. And sometimes they will say, just like this, without doing any algebra, which one of these is likely to be true. Now, we could do the math, and I think you should be prepared to do the math, because I expect that you have that level of algebra capability. But this one said specifically not to, and just decide which one of these equations is better. There's a clear answer as to which one of these is better. Now, let's talk about a few things. V is in the numerator of both. Can we use that as our reason? Let me give you an idea. If the velocity of the block was greater, would that compress the spring more? All right, the blocks were going faster, would they push the spring in more? Both of these equations say that that is true. Do you see that? Because it's on the numerator. So if V gets bigger, D gets bigger, we would not be able to use that as our explanation. I'll also point out that if the block was heavier, it would be harder to stop. I'm not sure we could use that as our explanation either, because it's in the numerator here and in the numerator here for block A. That one might not be a good explanation either. Your explanation probably should center around K. I think K is the best one. K is clearly in the denominator, in this one and in the numerator here. In one case, when K gets bigger, the distance the spring is compressed also gets bigger. Does that make any sense at all? In the other one, when K gets bigger, the distance the spring is compressed gets smaller. Does that make sense? If nothing else, you are supposed to be solving for D. This has got to be on one side of the equation, right? When you solve for D, you will be dividing by K. So this has got to be the better relationship. It's got to be. And any of the things we've just talked about that relate K and D together is probably reasonable. You already did that here. All you're doing is using that to determine which of these two equations is correct here. Probably 2 points.
What would give us 40 seconds to get the second floor?
You're talking about G? Right here, this one? Okay. Explain which equation better supports your explanation for the compression distance. I would state that having K in the denominator is your support. And I think all you have to say is that as the spring became stronger, as K was bigger, case 1 shows the distance getting smaller. Saying that K is in the denominator is sufficient. Be able to spell the word numerator and denominator. I know it sounds silly, but that's what they want. I had a conversation. Was this one tricky? Which is the solid line, case 1 or case 2? Case 2, how do you know? That's right, it's the distance. It doesn't go as far. It's that simple. Who cares about the time? The time isn't part of this at all. It's just about which one went further before it bounced back. And the solid line is the one that doesn't go as far, so it has to be case 2. Yep?
I have a question on the last one.
Yes. Okay. The student uses their observations to correctly claim that the collision between the ball and the force plate is inelastic. Use the student's observation to justify this claim. I think that one's pretty easy. But maybe you need more guidance? Can somebody offer me what their reasonable justification is? Yes, ma'am.
This collision is inelastic because kinetic energy is lost, which is shown by the ball not rebounding up at the same height, showing that momentum is conserved.
Everything but that last sentence is perfect. I wouldn't say the momentum is conserved because we don't necessarily, it's not conserved. It has less momentum after it bounces off the plate. But it's inelastic because in this case, we know there's less kinetic energy after the collision. Now, the thing about the collision of the ball and the force plate is inelastic is hard because we can't see the recoil of the earth. So it's hard for us to know if momentum is conserved because we'd have to measure the momentum of the earth to do so. But we know it's inelastic because the ball has less kinetic energy. And saying what you said about it leaving the plate at a slower speed and that being able to be shown because it doesn't go as high, I think that hits all the points perfectly. So the observation was the height of the ball. You use the height of the ball to represent how fast the ball was going first when it hit the plate and when it left the plate. And then knowing that meant that there was less energy. If you said all those things, you should get full credit. Yeah?
Just notice I was so confused because the numbers didn't get printed when I did it. So it said M and M, and I was like, this does not mean it'd be elastic.
Oh, yeah, that would be a problem.
Yeah, but if the ball rebounded the same height as it was dropped, that would mean it was an elastic collision.
No, it'd be that the ball retained all of its kinetic energy. Yeah, I would probably use the word elastic to describe the collision, but I'll keep coming back to the fact that we don't know the rebound of the earth. Or in this case, the force plate. The plate could have absorbed something. It obviously did. So the ball didn't come back as high. Now, in the next case, you're asked to actually figure out the impulse, which means you needed to figure out how fast the ball was going when it struck the plate and how fast it was going when it left the plate. This we did do in class, but just as a reminder, this is like 1.5, and it hits the ground, and it bounces back up, and it's 1.1. I did this in first period. Do you guys want to work it out? Do you want to see the answer? I mean, I got 5.1 kilograms meters per second. So I did that by using the fact that the velocity is going to equal the square root of 2gh in each case. So in the first case, it's going downwards. And in the second case, it's recoiling upwards. I chose upwards to be positive. And so my initial velocity is going to be the square root of 2 times 10 times 1.5. And my final velocity, square root of 2 times 10 times 1.1. I don't know what these equal. I forgot. 5.48 meters per second. And what's this one? 4.7 meters per second. Now, the big thing that you guys tend to forget is direction. If I said that upwards is positive, then the final velocity, 0.5 times 4.7 minus the initial momentum, you have to purposely make that velocity negative here because it was going downwards when it hit the ground. And this gives you, I think, the positive 5.1 kilograms meters per second. We good to move on? Apparently there's another page. This is change in momentum. And I did mv final minus mv initial.
I forgot to cancel.
Oh. That will make a difference. You'll get like 10.2. In the case of this collision where all the masses are the same and we say it's elastic, the math kind of is super simple here because of this. Watch what happens. I'm going to cancel out all the m's. They're gone. And I'm going to cancel out all the 1/2s and m's. And I get, in this case, 4 equals v1 plus v2. And 16 equals v1 squared plus v2 squared. Now this part is still the same. v1 equals 4 minus v2. I still have to do this. It's the result that I want you to see. So 16 equals, and here we go, 4 minus v2 squared plus v2 squared. 16 equals 16 minus, multiply them together, double it, 8 v2 plus v2 squared plus v2 squared. 16s go away. And here's the thing. I get minus 8 v2 plus 2 v2 squared. Get rid of one of the 2's. Right, because there's a 2 and an 8. And I get negative 4 v2 plus v2 squared. So yeah, I have to factor. And I get v2 and 4 minus v2. So v2 equals 0 or v2 equals 4. But do you recognize that v2 now is moving the same speed as v1 was? If they're the same mass and it's perfectly inelastic, the first box stops and the second box moves. You can memorize that. And it might be worth memorizing. If they are the same mass, like billiard balls. You guys have seen that where you're playing, where people play pool and they hit one ball and it stops perfectly and the other one keeps going. Or how about those little things where they have the balls in a row and you pick up one and it hits the side and they all stay there and the other one leaves? You guys know what I'm talking about? And they go back and forth. Same thing. In that kind of perfectly elastic collision, if they are the same mass, the answer is always the same. If they are the same mass, one object stops and the other object gets the same velocity as the first one had. That only works if they're the same mass. Now, I'm pointing it out because I had time. Is it on tomorrow's test? I don't know. I don't remember. I don't remember what's on the multiple choice. I have to check them out again today. It's been a while. Yeah.
Do you have to show all of our work if
Nope. Unless you're expressly asked to do so. But if this were to show up, it would show up in the multiple choice. You follow along? Okay. This is the data recorded. You're asked to provide a reliable, or you're asked if the plate provides a reliable set of data points for the impulse of the ball. You would have to figure out the area under the curve to do that. This is force. This is time. Be careful. Units play a big role in determining whether you're going to get a good answer here or not. Kilonewtons. So that's thousands of newtons, 10 to the 3. Milliseconds is 10 to the negative 3 seconds. You need to put this in newtons and seconds. I did 1/2 sum of the bases times the height. Bless you. So the height was 4,000 newtons. And this base goes from 0.2 to 3, 4, 5, 6, 7 to 0.8. So that's 0.6 milliseconds. 0.1236 seconds. And the bottom one is 1 millisecond, so plus 0.001 milliseconds. 1 seconds. There we go. So 1/2 times 0.0016 times 4,000. And I believe that comes out to be 3.2 Newton seconds, or 3.2 kilograms meters per second. Is this a reliable way of taking data? Is 3.2 close to 5.1? I wouldn't think so. If my data collection tools did that, I would be frustrated. I would say, no, it's not good data. It's not reliable. Justify your answer. They're not the same number. Not even close. They're off by a lot. I mean, 40% difference. You could calculate the difference if you wanted, but that's a big difference.